Swayam Prabha. Digital India. Educated India.
Okay, today we'll be talking about linear velocity, angular velocity and robot dynamics. Now linear velocity and angular velocity of a rigid body you would have studied earlier, but we'll just go through them again. So we have a rigid body like this, and this rigid body is translating, it is having a linear velocity, and or it could be rotating, where a rigid body is rotating in space and it is having an angular velocity. And then we will look at robot dynamics, that is essentially when we are giving torque at the joint, then how do the links move, and we have to derive our equation of motion based on whatever is the input torque. That is our robot dynamics. So let us look at linear velocity, angular velocity, and in robotics we are specifically interested in trying to look at the relationship with respect to the rotation matrices, because we know we have a rotation matrix between two frames which are rotated with respect to each other, and with respect to that can we see how to represent the angular velocity in terms of the angular velocity matrix. So first of all, let us start off with linear velocity. So what we say, we have an object, let us say this is a rigid object, and this rigid object is moving with some linear velocity. Then first of all, when we talk of velocity, we have to specify with respect to a frame. So we again say that we have a global frame which is fixed, which does not move. Let us say my fixed frame is the frame A, and then we fix a frame B onto this object and say this is my point Q, which is expressed on my frame B. Okay, so let us draw it here and see what it would look like. So we have frame A which is here. So this is my frame A, and this is my x, y and z axis. So we have the x, y and z axis of my frame A. Now we have another frame which is rotated, and let us call it frame B, and this is my frame B which is rotated with respect to, this is my frame B, and we have a point there which is point Q, okay, on the rigid body. So now what we are going to see is, if I want to express the velocities of this rigid body in terms of the reference frame or the fixed frame A, then what all is required. Now something to remember here is that there is only linear velocities. So it is having linear velocity, and there is absolutely no orientation change. Okay. So there is no change in orientation between the two axis frames, and it is having a linear velocity. Now this we have seen earlier is the distance between the origins. So this is my A, if the point is P, then A P B org. So this is the standard way of writing, where the distance between the two origins of two frame A and B are written in terms of A P B org. Now so there are two possibilities here. The first possibility is that this body on which we have fixed our frame B is moving with respect to frame B itself. Okay, so there is a velocity here where the body is having a linear velocity which is expressed in frame B, and the other possibility is that the two frames A and B are also translating. So this is one possibility here, and there is another possibility here of having the velocities. So what we can write this as the velocity of A in terms of the point in the velocity of frame of the point Q expressed in frame A can be written as the velocity. This is the velocity which is changing because of the change in the origins. That means this part is changing. So this is moving, having a linear velocity, and the other velocity is because of a change of Q in B itself. So we have a rotation matrix to bring it to frame A, and this is my BVQ. So this basically means that this part of the velocity is because of the change in the distance between the origins, between here and here, and this part is because of the velocity of Q in B itself, and we are using a rotation matrix to relate it to frame A. So this is giving me the linear velocities of this rigid body on which we have fixed our frame B. So this is what we mean by a linear velocity. Now what about rotations? Now if you look at rotation, let us try and understand rotations like this, that I have a frame which is fixed again. So this is my frame A which is fixed. So, this is my frame A. Okay. So, this is my frame A which is fixed, which is not moving. So, this let us call it as frame B, and then we have another frame which is my frame B, which is having some other angle. Let us call it, so this is my frame B, and let us call this frame B. Okay, this is my frame B. So, this is my frame B. Now, if we say that A is the reference frame which does not move, and so A is my reference frame, A is the reference frame which is not moving, B is the frame which is rotating about an axis, and let us say that this is rotating about an axis, let us call this an axis here. So, B is rotating about this axis, and let us call it A omega B. So, frame B is rotating about this axis and frame A is fixed. Okay. So, now here the important, so frame B is rotating with an angular A omega B, right. Now, there is origins are same, and there is no linear displacement between the origins. So, now what we are trying to see is that if you can visualize from here, that if we have a point which is let us call this point Q here. So, this point Q which is given at this point here, let us call this point Q. Okay. Now, because this Q is fixed on frame B, so let us say Q point in frame B. Now, because frame B is rotating, what will happen is this fellow will start rotating about this axis, if you can imagine what will happen. So, because frame B is rotating about this axis with an angular velocity, this point Q will start rotating about this axis also. Okay. Now, that is quite clear. Now, so we have an angular velocity of frame B. Now, because this point B is rotating about this axis, it will also have a linear velocity component. So, when we are looking at it from point A, it would appear that this point Q is also having a linear velocity. Now, we need to compute what is the linear velocity, and let us see how that is done. So, let us look at this part again. So, essentially what I am saying is that let us have a point Q which is fixed on B, and this frame B is rotating. So, what we can see is that it is rotating like this and having a circle like that. So, as far as this point Q is considered, what is its linear velocity because of the rotation? So, let us derive it and see what it looks like. So, essentially this is my axis, okay, and this point was rotating about the axis. So, it is rotating about this axis like this, and let us say it is here, and this is my A omega B, okay, about which it is rotating. Now, there is a point Q which is here at time t. Okay. Now, this point Q is can be connected to the origin, and this is my angle theta. Okay. So, as far as the center is considered, we have the radius here which is this much. Okay. So, this is my point Q. Now, after some time del t, what would happen is this point will go here. Okay, it will go, this is exaggeration, but it is a very small point. So, Q t plus del t. Okay, so, this point will go here. Now, we are here. Okay. So, what we are saying is that this point is Q, at time t it is here, at time t plus del t it is there. Now, if we look at how much distance has been it has traversed from here to here, then essentially we can find that out. So, this is my so this is basically this is theta. So, what is this angle? This angle is omega into del t, is the small angle it has moved, right. And what is this? This is q into sin theta. Okay. So, this is q and that is sin theta, this is theta here. So, this is going to become q into sin theta, and how much is the angle it has moved? It is the angular velocity omega into the small instant of time del t. So, essentially how much distance it has moved is del q here, okay, and we can write that as del q, sorry. So, d of q or a very small increment del q is equal to r theta. So, r is q sin theta, and what is theta? Theta, the amount it has moved from here to here, that is equal to omega into dt. So, it is equal to q sin theta and then omega a b into d theta into dt, sorry, right. So, this is the distance del q which it has moved from here to here in time dt. Okay. So, this is the linear velocity, which is this is the linear displacement you can see from here, and this is because this body has been rotating about the axis by having an angular velocity a omega b. Now, if I see in terms of velocity, then if I divide both sides by your del t, then what we will be getting is a v into q, which is equal to a omega b cross of a q. Okay. Now, this is what we mean by the linear velocity, that is because of the rotation of a body having an angular velocity. Okay. So, what we can see from here is that although this point was rotating, this point q was rotating about this axis, it has a linear velocity component, which is given by this expression. Okay. And now, if it was also having a velocity in terms of q, then what we can write is a into v into q is equal to a r b into b v q plus a. So, the total velocity is equal to omega into b cross a q. Okay. So, essentially what we are seeing is that the point q could also be having a velocity in. So, the point q could also be having a velocity in frame b, which is taken care of here, and this is multiplied with the rotation matrix to bring it to the reference frame a, and plus it has this component of linear velocity because of the rotation. So, the total velocity will be this component plus that component. So, here we are basically seeing that an object which is rotating has linear velocity also because it is rotating about an axis, and the total velocities are given by this expression. So, using this expression for the linear velocities and this expression for the linear velocity because the object is rotating, we can find out what are the corresponding velocities. Okay. So, now let us look at. So, the other thing is what is the total velocity. So, the total velocity b of q is equal to a v b org if the two frames are also moving, plus a b r into b v q, which we just wrote, plus a omega b cross a q. Okay. So, this part is because of the rotation, this part is it has a linear velocity because q could be changing with respect to b, and then if the origins of a and b are changing having a linear velocity, then again this component will come inside. So, we have three components added together, and this gives you your total linear velocity. Okay. So, now let us look at so in robotics we try to correlate the velocities with respect to the rotation matrix. So, what we will try and see is that the rotation matrix has some properties, and how can we talk about rotations in terms of the rotation matrix or angular velocity in terms of the rotation matrix, and that is what we do next. Let us look at property of rotation matrix. So, the rotation matrix has a lot of interesting properties. We have seen that the determinant is equal to 1, then each of the columns is having a mod of 1 because they are unit vectors, and then the inverse is equal to the transpose. So, apart from that, we can also express the rotation in terms of the rotation matrix, okay, the angular velocities in terms of the rotation matrix. Now, we look at this r into r inverse is equal to I, this we know because for any matrix this will hold. Now, if you write this as r into r transpose is equal to I, essentially because your r inverse is equal to r transpose. So, R is a proper orthonormal matrix. So, this is a proper orthonormal matrix, and hence its inverse is equal to its transpose. So, now we can write this expression. Now, if I take the derivative of this expression, then we can write it as r dot into t plus r into r dot t is equal to 0. I can write it this way. So, we take the derivative of this one first, then we take the derivative of this, and this is an identity matrix. So, the derivative is 0. Now, if I further write this as r dot into r transpose plus r dot into r transpose okay, is equal to 0, then also it holds because you can see that this part here is equal to this part. Okay. So, essentially r dot transpose can be written this way, and so we see that this and this is the same now. So, I can say that S plus S transpose is equal to 0. Okay. And this S matrix is called a skew symmetric matrix, is a skew symmetric matrix, and the property of the skew symmetric matrix is that S plus S transpose is equal to S plus S transpose is equal to 0, and this skew symmetric matrix is also called the angular velocity matrix. Okay. So, we see that our matrix S, which is equal to R dot into R transpose, is a skew symmetric matrix, and it is called the angular velocity matrix. Now, can we go further and look at the rotations in terms of the rotation matrix? So, we know that the velocity of a point, so we can express the rotation matrix. So, the rotation matrix expresses the coordinates, expresses or relates the coordinates from a rotated frame to a reference frame, to the reference frame. So, we have a frame AP, we have a frame A, and we have a point P, which is the fixed frame. Then we can say that if the point P is expressed in another frame, let us call this BP, then they are related in terms of the rotation matrix. So, essentially when we derived it, we said that we have two frames again, A and B. This is my frame A, this is my frame A, which is not moving, and we have another frame which is frame B, which is rotated by angle theta. Okay. So, essentially if you have a point there BP, which is expressed in frame B, then what is its coordinates in frame A is given by this equation, right. So, essentially this point, if it is equal to UVW, we want AP will be equal to XYZ, and what is the correlation between UVW and XYZ is given by the rotation matrix. Now, in this case, this gives us the position of the point P expressed in frame B in frame A when we multiply this with the rotation matrix. Now, basically what we are trying to see is, can we come to the velocities, can we come to the angular velocity from here? So, what we do is we take the derivative of AP. So, we take AP dot is equal to, we take AB R dot into BP. So, I take the derivative. Why do I take the derivative? Because I want to take the angular velocity, I want to find the velocities, right. So, this is basically giving me AP, the velocity of the point P expressed in frame A. Now, BP from here, we can express BP in terms of, so we saw that AP is equal to A BR into BP. Now, if I want to find what is BP, then what I can do is I can say BP is equal to AB R inverse into AP, right. So, I take this and I put it in place of BP, and we have A RB into R inverse into AP. Okay, sorry. Okay. Yeah, so I put it here. So, what we get is that now we get this R dot into R inverse, which I can write as A into VP is equal to R dot into R transpose into AP. I have left the subscripts of A and B, you know what it means. It means basically B with reference to A. Now, if you see what we just derived some time back, that this matrix R dot into R transpose is the matrix S. So, this is my skew symmetric matrix S, and this skew symmetric matrix S is exactly coming out here as R dot into R transpose. This is my S matrix, the skew symmetric matrix S. So, essentially we can derive it this way, or we can derive it this way, or we can derive it this way, and what you basically find is that we find it is A VP is equal to skew symmetric matrix S into AP. Okay. Again, this fellow is called the angular velocity matrix, where this is called the angular velocity matrix. Okay. So, we have seen basically that when the body is moving in space, it can have a linear velocity and it can have an angular velocity, but because of this angular velocity, it also creates a linear velocity on the body, and this angular velocity can be expressed in terms of the angular velocity matrix, which is the skew symmetric matrix, and which in turn can be represented by the rotation matrices. So, we see that the rotation matrix not only gives us the a relationship in terms of the position between two frames. It can also be, it is also useful for expressing the angular velocity when it is moving. Okay. So, next let's look at in a robotic system essentially velocities move. So, what do I mean by this is that in the last class or a couple of classes back we looked at how force moves. So, essentially if my arm is moving, so I see my arm and my arm is moving, then essentially how does this arm move, right, if you think about that. So, we have muscles. In the case of robot there is a motor. So, when we give a torque, a joint moment or a torque to this joint, then this joint moves. Now, this joint moves means there is a change of the position, there is a change of the velocity, there is a change in the acceleration. So, when this is moving there is a position change, velocity and acceleration of the respective joints. Okay. So, this is how the joint moves, and when we study dynamics we see what is the equation of motion when we give a particular input torque. Now, here what we are trying to say is that essentially I want to find out that when this arm is moving, when this joint is moving, whatever is the velocity here, it will tend to propagate in this direction. We saw that forces propagate. So, when I am pushing something, whatever is the force on my palm is go from this joint, it will come to this joint, then it will come to this joint. So, forces move in this direction, okay, from the nth link to the base link, whereas velocities move in the reverse direction. So, when I am giving a velocity here, essentially this velocity from here will be transferred onto this one and then it will go onto that one. And we want to see what is this velocity transfer from link to link. Okay. So, it essentially is very important to know that there is a transfer of forces and velocities which are going on. Now, why is it important? It is very important from the control point of view. We will come to control systems, then we will see that, for example, if this joint is moving but this joint is not moving. So, it would appear that because this joint is not moving, it is not subjected to any forces or torques, but because this joint is moving and these velocities are moving in this direction, what would happen is this will also be subjected to some torque now. Okay. So, this is something that is important to see, that forces move from the outward link to the base link and the velocities move from the base link to the outward link. Now, let us look at how the velocities and velocities move. So, let us look at this very general example here. So, we have a link, again this link is drawn in 3 dimension. Okay. So, this is a 3D link. 3D link means it can have any shape, and let us look at, so this is a 3-dimensional link. So, there is a link here and there is another link there which is in that direction. Okay. So, this is 2 links. So, there is another link here. Now, what we are saying is that we start off by assigning our axis. So, we have assigned our axis. So, the first one is my z axis. So, let us call this my zi axis. So, this is zi, and the next fellow has the next axis is my next axis is zi plus 1. Okay. Now, there is also an x axis. So, we can draw our x axis here. So, this is my xi, and there is similarly an xi plus 1 on the other side. Okay. Now, what we are saying is that let us say that this link is subjected to a velocity omega I. Omega I basically means the angular velocity expressed in frame I. Similarly, this joint here will be expressed to let's put the z that side. So, let us put the zi plus 1 there. So, what we are saying is this fellow here is subjected to omega I plus 1. So, this is the angular velocity expressed in frame I plus 1. Now, and there is a distance between them. So, there is a distance between this is pi plus 1. Okay. So, now we are saying is that because there is an angular velocity here, this velocity will tend to propagate from ith link to the I plus 1 link. So, velocities will propagate from I to I plus 1th link. And because there is a distance between the origins, between the axis and the origins of I and I plus 1, and the distance is pi plus 1, what will happen is this will be subjected also, this will also experience a linear velocity. That is something we just saw, that this is a point which is moving about this axis, and hence it will be subjected also to it will also have a linear velocity. So, we would like to find out that when the velocities are moving, how do they propagate from one link to another link. Okay. So, as you can see, this link has velocity omega I, this fellow has omega I, this one has omega I plus 1. So, when the velocities propagate, this link here will have the velocity of the previous link, it will have I plus 1 plus its own velocity I plus 1. Okay. So, essentially link I plus 1 will have 2 velocity components, it will have omega I plus it will have omega I plus 1. I will just write down the complete, this is just to understand, and the linear velocities are also going to move. Okay. So, now what we are saying is here that essentially because of this omega I here, this omega I will have an effect on the next link also, plus the link of the I plus 1 will have its own velocity, which is omega I plus 1. Okay. So, if you write it like this, omega I and I plus 1. Okay. So, this is the velocity of the link I plus 1, which is equal to omega I, the velocity of the previous link, plus r I to I plus 1, that is the rotation matrix, which is taking it from I to I plus 1, and theta dot is I plus 1 and z I plus 1, this is my direction. Okay. So, here what we are trying to say is that, or what this expression tells us is that the velocity of the next link, which is I plus 1, is equal to the velocity of the previous link, which is the ith link, plus its own velocity, which is equal to theta I plus 1. And the two frames I and I plus 1 could have a rotation between them, and hence we are putting a rotation matrix there to correlate it. And this is the axis about which the angular velocity is there. Now, this is expressed in frame I. So, this is expressed in frame I, and this is the way of writing that it is the velocity of the I plus 1th link expressed in frame I. Okay. Now, what about the linear velocities? The linear velocities will basically be of the ith frame is equal to the linear velocity of the previous frame again, plus there is a linear velocity omega I cross p I plus 1. Okay. This is what we are talking about, that this velocity component will come because there is a rotation involved here. Okay. So, what we just expressed some time back, that is this expression here, is basically telling us that this component is coming because there is a rotation. Okay. And that component is being shown here, omega cross p I plus 1. Now, I want to express this in frame I plus 1. So, velocities in I plus 1, because they are moving forward, right. So, what I do is I multiply both sides by the rotation matrix r I plus 1 to I, which is the inverse of I to I plus 1. I multiply both sides by this matrix and convert it to I plus 1. Okay. So, I multiply these two equations, and then what we get is omega I plus 1 is equal to r of I plus 1 I. Please note that this is an inverse matrix here, into omega I plus theta dot I plus 1 into z I plus 1. Okay, this remains the same. So, essentially this is expressing the velocity, the angular velocity in frame I plus 1. Now, next for the linear velocity, so this is our equation number 1. Now, for the linear velocities, again we multiply and we say that linear velocities in its own frame, or I plus 1th frame, is equal to r of I plus 1 into I into V I plus omega I cross p I plus 1. Okay. So, this is my equation 2. So, this gives us the two velocities, the angular velocity and the linear velocities expressed in frame I plus 1, okay, or in its own frame. Okay. So, using these two equations 1 and 2, we can move from link to link. So, what we are seeing here is that the velocities propagate, and because they propagate, the velocity of the next link will tend to get added on, the velocity of the next link will also have the velocity of the previous link included. Okay. And this is what these two equations show us. So, using these two equations, we can go from link to link, and let us have a look at an example in which we can understand this better. So, essentially what we can understand here is, let us look at this example and it will become clearer. So, we have one link here and we have another link here. Okay. And okay, so this is my base link. Now, this is my x0 and z0 and z1. Z0 and Z1 are here, Z2 is here, okay, as per DH conventions, Z3 is there. So, x1 is here, x2 is here, and x3 is on this side. So, x3 is there. Okay. Now, suppose we say that this is subjected to an angular velocity theta 1 dot, and this is subjected also to an angular velocity. So, link 1, so this theta 2 dot. Okay. So, this has link length L1 and this is link length L2. Okay. So, link 1 which has length L1 has angular velocity of theta 1 dot. So, link 2 has length of 2 and it has angular velocity theta 2 dot. Okay. So, now we want to find is what is the velocity of the third axis here. Okay. So, find velocity of axis 3. Okay. So, my axis 3 is that origin of axis 3 is at that point. So, I want to find the velocity of this point P, let us call it point P, velocity of axis 3, or we can call it point P. The origin of axis 3 is point P. So, how do we proceed? Essentially we are seeing that the velocities are going to propagate and we want to find out how the velocities move from link 0 to 1, 1 to 2, then 2 to 3. And exactly what we do is essentially we just use these two equations. These two equations gives us the relation between the previous link I and the next link I plus 1. The angular velocity is given by the equation 1 and linear velocity is given by equation 2. So, we just use these equations and find out how the velocities are moving. Now, we see that there is a rotation involved between the axis here. So, because there is a rotation involved between the axis, we first find out our transformation matrices T 0 to 1 is given by. So, when joint 1 moves, what would happen is you have cos, there is a rotation about z axis. So, it is cos 1 minus sin 1 and sin 1 cos 1, and this is 0 0 0, this is 0 0 and that is 0 0 0 1. Okay. So, our first matrix is this, which is relating frame 1 to frame 0. The next matrix is 1 to 2, which is relating frame 2 to frame 1, and if you look in this figure, frame 2 is here at this point and frame 1 is there. So, essentially it is cos 2 minus sin 2 cos 2 0 0 1 0 0 0 0 0. So, we see that the origins of the two frames 2 and 1, there is a distance between them. It is L1 in the direction of x axis. So, it is 0 0 1 and it is 0. And the third one, if you look very carefully at the two frames of the second frame and the third frame, the x axis are in the same direction, the z axis are parallel. So, there is no angle between them and hence there is an identity matrix there, but only the origins are different. So, essentially what we get is an identity matrix there 0 0 1, this is 0 0 0. So, this is L2 0 0 1. So, this three transformations gives us the relationship between the frames, which is taking it from the frame 0 or the frame 1 to the frame 3. Okay. So, these are the transformation matrices. Now, where are we going to use these transformation matrices? We need these transformation matrices here. Okay. So, we are going to use these matrices when we are going to compute the velocities. Now, let us start off by using this. We will start off by using the angular velocity. So, angular velocity of the next link I plus 1th link is equal to angular velocity of the previous link, which is I, plus its own velocity, which is given by theta dot I plus 1. The linear velocity V I plus 1 is equal to the rotation matrix inverse. Please note that this is an inverse matrix, is equal to the velocity of the previous link plus the linear velocity because of the rotation, okay, which is coming from here. So, let us proceed. So, let us look at this again. So, this is rotating with theta 1 dot angular velocity. Okay. So, we are given that theta 1 dot omega I. Let us start off with the first one, omega I is equal to 0 0 theta 1 dot. This is given that the first joint is rotating. So, this is the first joint. Please see this, that the origins are the same and the first axis is rotating with respect to the fixed axis 0 axis and is rotating like this about the z axis, and the angular velocity is theta 1 dot. So, the first case becomes omega I of the first link becomes 0 0 theta 1 dot. So, this is my 0 0 theta 1 dot. Now, what about the linear velocities V I, V 1 1. Now, if you look at the linear velocities again here, let us look at the linear velocities here. So, linear velocity says is the velocity of the previous link. Now, velocity of 0 is not there, the 0 link is not moving, it is a fixed link. So, this is 0. Again, this component, there is no distance between the origins and hence this component is 0 and hence the velocities are going to be 0. So, if you look closely here, essentially link 1 and link axis 1 and axis 2, the origins are the same. Okay. So, there is no distance between them, and hence this velocity will become 0 0 and 0. Okay. So, for the first link we get angular velocities and linear velocities. Next we want to find the velocity for the second link with respect to itself. Okay. So, this basically means velocity with 2 to 2 means 2 is the link number and 2 is the axis number. So, it means the link 2 with respect to itself. So, let us go to the angular velocity here. So, the angular velocity will be the angular velocity of second link will be angular velocity of first link plus the angular velocity of the second link, which is given here. So, essentially you can add them and it will become 0 0 theta 1 dot plus theta 2 dot. Okay. So, this is giving us the angular velocity of the second link. Now, if you look at the angular velocity of the the linear velocity of the second link, which is this. So, this is equal to what? Now, this is equal to, let us use the equation again, and this is equal to the rotation matrix into the velocity of the previous link, which is not there, plus this component, which is so this component is going to come because omega I is there, omega 1 is there, and there is a distance of L between the two axes. So, how do we write that? And we also see that there is a rotation angle between both of them, okay, between axis 2 and axis 1. So, x 1 is this side and x 2 is that side. So, there is an angle between them also. So, we are going to use a rotation matrix. So, we will use this rotation matrix, the inverse the rotation matrix here. We are going to see the velocity of the previous link plus this is because of the rotational velocity. So, let us look at what this will happen. This will be C 2 plus S 2 minus S 2 C 2 0 0 1, this is 0 0, and what is the so what is this component? So, what is this component? Omega I cross pi. So, omega I cross pi is essentially 0 0 0 L 1 theta 1 dot and this is 0. Okay. So, let us go back and look at this again. So, omega cross pi. So, what I am basically finding is omega cross pi. So, what we are saying is that how did we get it? So, if I take the cross product, it is I j k. Okay. Omega I is the of the omega I is omega 1 here. So, which is equal to 0 0 theta 1 dot, okay, and x is along, and what is pi? Pi is the distance between the two axes. So, pi is the distance between this origin and that origin, which is L 1. Okay. So, this is becoming L 1 in the x direction. So, it comes out like this, and if you do this, what we will be getting is this term, right. So, what we will be getting is 0 L 1 theta 1 dot and 0. That is how we have got it. And if I open it up, what we will be getting is you can just open that, and what we will be getting is L 1 S 2 theta 1 dot, and we will be getting L 1 C 2 theta 1 dot and 0. So, I hope you understand how we got this one. Okay. So, this is the angular velocity of a second axis, this is the linear velocity of the second axis. Now, from here we need to move on to the third. So, for the third one, again let us look very carefully here at the figure here. Now, what we can see here is that the second axis and the third axis, the x axis are the same, means there is no rotation between them. So, it is an identity matrix and they are rotating about the z axis. So, essentially what we can write here is that omega 3 3 is equal to omega 2 2, and we know what is omega 2 2. So, we know what is omega 2 is equal to this one only, okay, because the third axis you can note here does not have any additional velocity, it does not have any additional angular velocity here. So, its angular velocity is essentially because of the velocity of the first joint, first link and the second link, okay. It does not have any velocity by itself, and hence when we are using this equation, essentially it does not have its own velocity. So, this part of own velocity is not there, it only has the velocity of the previous link, and this becomes equal to omega 3 3 is equal to omega 2 2. Now, what about the V 3? V 3 3 becomes equal to, we can find the values of V 3 3, and how do we find the values of V 3 3? We can basically say that V 3 is equal to V 2, which is the velocity of the previous link, plus this angular velocity vector which is coming in because of the rotation. So, if you do that, what we find is it is r into, it will come out as, we can write it straight as L1 sin 2 theta 1 dot and L1 C2 C1 sorry. So, this is theta 1 dot plus L2 theta 1 dot plus theta 2 dot and 0. Okay. So, how did we get that? Essentially what we are doing is we have just used this equation. It says the velocity of the previous link, which is link which is joint number 2 plus the angular velocity there, and joint number 2 had a velocity of you can see this is the joint 2 velocity, okay, or the axis 2 velocity plus the angular velocity which is coming out of here. Okay. So, it is this plus this. Okay. That is what we have got. So, by this we are able to see that this is the velocity. Now, something to be very to note very carefully here is this is velocity of point 3 sorry, it was point P or origin of axis 3 or origin of axis 3, okay, with respect to itself or with respect to axis 3 itself. Okay. Now, if I want to express this velocity of P in base frame 0, in base 0 frame, then all I need to do is to multiply it with the rotation matrices. So, velocity of 3 with respect to 0 is equal to the rotation matrices 0 to 3 and V 3 3. Okay. So, this velocity is expressed in axis 3. Please note this very carefully that this is axis 3. Now, if I want to express in axis 0, then essentially I need to multiply with the rotation matrices, which will take it in R 0 3 you know by now is equal to R 0 1 into R 1 2 into R 2 3, right. So, this total matrix we can multiply and we can express in frame 0. Okay. So, next what we need to look at, so we know how to get angular velocities and linear velocities. Now, what we need to look at is to move forward and get or look at what are the joint torques and the equation of motion. So, what we mean by that is essentially we have seen the force propagation from the top, the forces come down, the velocities move from the base link to the forward link. Okay. And how does the robot work? Essentially there is the joint torque is provided to the joints, and because of that joint torque the link is going to move. Okay. So, there will be some equation of motion. So, basically what we want to find out in dynamics is that what are the forces required to cause motion. So, what we need to know in dynamics is essentially what are the forces required, forces I would mean torques or moments required to cause motion, and the equation of motion of a manipulator. Okay. So, dynamics will give me both of this because that is required from the control point of view. So, when we are controlling the manipulator, we have a controller and the controller needs to know how much torque to give to the motor, and that would depend on what is the forces, and that would depend on the kind of motion that is desired at the end effector. Okay. So, let us look at dynamics now. So far we have been looking at kinematics. Now, let us look at dynamics. Okay. So, what dynamics is essentially, let us look at this before we proceed. Let us look at this table here. So, we have this table which is having the two components. So, there is no force. So, let us say no motion. So, in robotics let me write it here. We study about motion, something is moving, and we study about force. Okay. So, when something is moving, then we are looking at the motion of the structure or the linkage or whatever. When a force is being applied, we are doing the force analysis. Now, if you are doing an analysis in which there is no motion, there can be no motion or there can be motion. Okay. So, this is just a table correlating this force and no force, and there can be no force and there can be force. Okay. So, if you are looking at an analysis in which there is motion, but there is no force, then this analysis is basically called kinematics. So, kinematics is the study of motion, but where we do not worry about the forces. So, whatever we have been doing till now is basically kinematics. Now, if you are looking at force, but no motion, then we are talking about statics. So, statics is the force is the study of force, forces which are getting transmitted, force, reaction forces, etc., when there is no motion. Okay. Say for example, when you are studying a bridge does not move. So, you will probably be doing static analysis, whereas for a robot which is moving, we will be doing kinematic analysis. Now, if you are looking at motion and you are looking at force together, then basically this is called dynamics. Okay. So, what will be so far what we have studied is we looked at statics. From statics we saw that we are talking about the joint torques tau is equal to J transpose into F. This is what we found, that the end effector forces are related to the joint torques by the transpose of the Jacobian, and this is the static force analysis. Okay. So, the system is not moving. Now, in kinematics we saw the relationship between the forward kinematics, inverse kinematics, relationship between end effector x y coordinates is a function of your joint angles thetas. Okay. So, that is your forward kinematics, inverse is the inverse of this equation. Now, in dynamics basically we are looking at the effect of position, velocity and acceleration, and we are looking at the inertia, the mass or the inertia of the links to move it. So, dynamics is essentially torques required to get a desired motion, to get desired motion of the end effector. So, this will so the dynamic analysis essentially tells us how much torque is required at the joints to get a particular kind of motion at the output. Now, so dynamics has to do with position, velocity and acceleration, and what is moving is a rigid link, which is a body, it has mass. Now, when we talk about mass distribution, so we can talk about mass distribution of a body. Now, when we talk about in one dimension, so 1 DOF, one dimension, we basically talk about mass of a body. Okay. So, if you have something moving on the table, we can talk about the mass of the system. Okay. So, we have for example, this pen which I have kept on this table, and I am pushing it with some force, then you know force is equal to mass into acceleration as per Newton's law. Right. Now, if there is something which is rotating, okay, so this object is rotating or it is fixed here and it is rotating, then we can talk about in 2D. So, in 2D, so in rotations we can talk about the moment of inertia, Okay. So, when something is rotating, we can talk about the moment of inertia about an axis. But the moment you are coming to 3D objects, okay. Now, this 3D objects can have rotation about any axis. So, for example, if this is a 3-dimensional object, then this can rotate about this axis, it can rotate about this axis, it can rotate about any other axis, about this axis it can rotate about any axis, right. So, basically we have to your mass and moment of inertia is not enough to describe or to characterize the motion of the body, and hence what we use is essentially the term inertia tensor. Okay. So, we use an inertia tensor in 3D, and this characterizes. So, the inertia tensor essentially characterizes the mass distribution of the body. Of the 3D body, 3D object. Okay. That means, if you have to rotate about some axis, what is the approximate energy that is required. So, that is characterized by the inertia tensor of the body. Okay. So, here we are talking about a robot link in 3-dimensional space, and hence we have to talk about the inertia tensor. So, let us look at very quickly before we proceed to our actual dynamics, that what an inertia tensor looks like and what it means. So, essentially an inertia tensor, so we are talking about an inertia tensor. So, this inertia tensor can be explained this way. So, this is my x axis, y axis, and that is my z axis. Okay. So, if you consider a very small volume in there, let us call it dV the very small elemental volume in here, okay. And let me call this elemental volume dV. Then what I want to know is, if I am going to rotate this elemental volume about the x axis, how much energy is required, okay. And if I am going to rotate about the z axis, how much energy is required, and about the y axis, how much energy is required. Now, I can rotate about any axis, as we said. So, if there is a cross axis, then also we need to find out what is the energy required. So, essentially I can define the inertia tensor as I xx minus I xy minus I xz, and this is I xy, I yy, and this is minus I yz. This is equal to I xz, and this is I yz, and this is equal to sorry, this is minus, and this one is I zz. So, essentially the inertia tensor, very generally speaking, tells you that if you want to rotate about any axis, how much torque is required, okay. And so, and hence it characterizes the torque required to move about any axis, and in 3D cases we talk about this inertia tensor, right. And how is it defined? So, essentially you can figure out that if I say that my object is going to rotate about the x axis, then I am going to say I xx is equal to, you can see here how far this object, this elemental volume is from the x axis and y axis, would actually represent how much energy is required to rotate about the x axis. So, this is given as this is a very general, very crude way of explaining it, x squared plus y squared divided by rho dV, okay. This is rotation about x axis, and this is my this is rotation about y axis. So, it is volume of x squared plus z squared into rho dV. Similarly, I zz is equal to triple integral of x squared plus y x squared plus this is x squared plus y squared, this is equal to y squared plus z squared, x squared plus z squared, and this is equal to x squared plus y squared, and so this is equal to z squared plus y squared, z squared plus y squared, because essentially it is a distance from here and the distance from there. So, it is z squared plus y squared, okay. So, this is equal to rho into dV, okay. So, this gives us the mass distribution about the principal axis x, y and z. Now, if it is rotating about any other axis, that is what we mean by the this is called the mass moment of inertia. This is the mass moment of inertia, okay. So, these 3 terms are called the mass moments of inertia, and the remaining 3 terms, remaining 6 terms, these are called the products of inertia, mass products of inertia. So, how do we define them? We basically define them as I xy is equal to integral of xy rho dV, I xz is equal to triple integral of xz rho dV, and I yz is equal to integral of yz rho dV, okay. So, what is rho? Rho is the density, and dV is the elemental volume, and dV is elemental volume, okay. So, this characterizes the mass distribution of a body, and so this is called the mass products mass moments of inertia. This is called the products of inertia. So, this is called the mass products of inertia. Okay. So, now let us look at a very simple example in which we can look at how to compute this before we proceed, because for the links we need to compute the products of inertia and the mass moments of inertia. So, we need to know how to compute them. So, let us look at an example where this is my x axis, this is my y axis, and this is my z axis, and we have an object which is like this. So, this is my object which is kept here. So, I have kept my object here, okay, and it has the dimensions of the object are given by, this is the height h, this is w, width and length is L, okay. So, I want to compute my moments of inertia here, and so the first one I am going to compute is Ixx, okay, which is given by the triple integral. Okay. So, 0 to w, 0 to L and 0 to h, the 3 length, width and height, and this is y squared plus z squared, which is equal to rho, remains as rho, elemental volume. So, when we looked at the elemental volume, this is equal to dx into dy into dz. So, it is an elemental volume. So, I write dx into dy into dz. So, if I integrate this, what we get is m by 3 L squared plus h squared. So, this is very simple, you can do the integration, and similarly for so we can correspondingly find using the same procedure we can find for Iyy and Izz. So, this can be done very easily, and we also need to find for the I your Ixz, which is the product of inertia, or Ixy. Let us look at the Ixy example. So, this is computed just for example 0 to w, 0 to L and 0 to h, and this is xy rho dx dy dz, and this comes out to be m by 4 w into L. Okay. Similarly, you can compute for Ixz and Iyz. Okay. So, this computation you can do, right. So, what we have seen here is that we are talking about the inertia of a body, okay, in 3-dimensional space, and the mass distribution of that is an indicator of how much energy is required to move about some axis, about any axis. Actually, this is motion about the principal axis, and the others are motion about the cross axis. Now, let us look at the definition of. So, let us look at the definitions of dynamics, and let us look at how we are going to use all this for. Now, there are, so dynamics is basically trying to find out the forces causing motion, forces or torques causing motion, and we want to find out the equation of motion, due to a force, or torque. Okay. And dynamics can be done in by using different methods. The first one is we can use Newton-Euler. So, we have Newton-Euler. Okay. Now, Newton-Euler method is basically a force based method. So, we use Newton's laws of motion, force is mass into acceleration, and move in the outward direction and the inward direction. What I basically mean is I see what is the forces acting at the joints. So, if I have an end effector force, the forces are going to move backwards and the velocities are going to move outward. So, there is 2 loops which goes on, we call the outward loop and the inward loop, and they basically to compute the forces. So, I need to find the velocity, accelerations, and then using Newton's law I can find what is the force acting, forces acting. So, this is one way of doing it using Newton's law, force is mass into acceleration, okay, or so basically I need to find what is the what is x dot and what is x double dot to use Newton's law, and this we can find from propagation of velocities from the base frame to the top frame. Okay. The second method is Lagrangian-Euler, in which we use this is an energy method. Okay. So, the Newton-Euler method is an energy method. It basically defines, it finds out the difference in the kinetic energy and the potential energy. So, we have a kinetic energy minus potential energy, and then it puts it into the equation d dt of dl by d theta dot minus dl by d theta is equal to tau to get the torques acting at the joint. So, essentially this gives us this is an energy method in which we define a scalar function Lagrangian and then use it to find the torques acting at the joints. So, these two methods we will be looking at. First we will be looking at the Lagrangian-Euler method to find the torques acting. Now, let us look at the Lagrangian-Euler method a little bit. So, we start off by looking at Lagrangian Euler. So, we will start off by looking at Lagrangian Euler method, in which we are going to define the kinetic energy and the potential energy. So, we are talking about the kinetic energy of a body is given by half mass into V transpose V plus half omega into I omega. Okay. So, this is the kinetic energy of a body, and we are talking about the potential energy. So, let us call this U, which is equal to m mass into mg into pi plus u ref, which is the reference potential energy. So, this is the reference potential energy. Okay, so next class we will be continuing about the Lagrangian Euler dynamics. So, we stop today. So, thank you.